In this lecture, let's focus on the Lagrangian formulation of classical mechanics. In the previous lecture, we got introduced to degree of freedom. We were saying that degree of freedom is the number of generalized coordinates, and generalized coordinates of a system is the natural minimal complete set of variables by which we can completely specify the configuration of that system. Of course, such variables will be independent. Now let's get into the definition of generalized velocity. Generalized velocity is the total time derivative of generalized coordinate. And generalized coordinates are denoted by qi, and generalized velocities are denoted by qi dot. So the dot here represents the total time derivative. Now, generalized coordinates and generalized velocities, as you know, they does not make any difference between positions and angles. So qi can be x, y, or theta. That does not make any difference between positions and angles, and also they can be even a thermodynamic variable, or it can be even charge. So this is not particular to any field. And generalized velocities corresponding to x, generalized velocity is x dot, corresponding to y it is y dot, corresponding to theta it is theta dot, and corresponding to charge it is current, because if you take total time derivative of charge you will get current. Now in Lagrangian formulation, it is assumed that the generalized velocity does not depend on generalized coordinate. That means if you take partial derivative of del qi dot with respect to del qi, this is equal to 0. Even I can be different as well, so here it can be j as well. So del qi dot divided by del qj is equal to 0, and del qj divided by del qi dot is equal to 0. So they are not dependent on each other. This is an assumption that we make in Lagrangian formulation. Now let us define Lagrangian. Lagrangian is a suitable function. Lagrangian is a suitable function of generalized coordinate, generalized velocity, and it can be a function of time as well. Now what do we mean by suitable function? By suitable function we mean that if we place this function in Euler Lagrange equation of motion, then we should get the correct equation of motion. It should describe the dynamics of the system correctly. Then it is a suitable function. And Lagrangian is not unique. L is not unique. Lagrangian is denoted by L. It is not unique. And Lagrangian does not have any physical importance. So if someone asks you what is the dynamics of the system, you cannot tell about it by looking at the Lagrangian. You have to put the Lagrangian in Lagrange's equation of motion, and then you will obtain the correct equation of motion, which can be used to tell about the dynamics of the system. In most cases, we can write Lagrangian is equal to kinetic energy T minus potential energy V. But this is not the case always. Now I will discuss one example where Lagrangian is equal to kinetic energy minus potential energy, and one more example where Lagrangian is not equal to kinetic energy minus potential energy. In the case of simple harmonic oscillator, in one dimension, we have kinetic energy is equal to half m v square, half m x dot square, and potential energy is equal to half m omega square x square. And Lagrangian of simple harmonic oscillator in one dimension is half m x dot square minus half m omega square x square. So this is a case in which Lagrangian is obtained by simply subtracting the potential energy from kinetic energy. Now consider the case of a free relativistic particle. Relativistic free particle. In the case of a relativistic free particle, kinetic energy is equal to total energy minus rest mass energy, which is equal to m naught c square divided by root of 1 minus v square upon c square minus, so this first term is total energy minus rest mass energy is m naught c square. So this is the kinetic energy. Now for free particle, potential energy is equal to 0. Therefore a Lagrangian is equal to, if Lagrangian is equal to t minus v, this should be m naught c square divided by root of 1 minus v square upon c square minus m naught c square. But if we put this Lagrangian into the Euler Lagrange equation of motion, then it does not produce the correct equation of motion. It does not describe the dynamics of a relativistic free particle. Therefore, in the case of a relativistic free particle, L is not equal to t minus v, because it does not describe the dynamics of the system correctly. In order to get correct equation of motion, Lagrangian is equal to minus m naught c square into root of 1 minus v square upon c square. So this is the Lagrangian of a relativistic free particle. Now let us discuss what generalized momentum is. So generalized momentum is denoted by Pi. Pi is equal to generalized momentum. This is also called canonical momentum or conjugate momentum, and it is denoted by Pi. This is equal to del L upon del Qi dot. So generalized momentum is the partial derivative of Lagrangian with respect to generalized velocity. So this is partial derivative with respect to partial derivative of Lagrangian with respect to generalized velocity. For example, if Qi is equal to x, then Pi is equal to del L upon del x dot. If Qi is equal to theta, then P theta is equal to, this is Px. Px is equal to del L upon del x dot. P theta is equal to del L upon del theta dot. Del L upon del theta dot. Now generalized coordinate and generalized momentum, these are canonically conjugate variables. These are called canonically conjugate variables. Canonically conjugate. Why they are canonically conjugate pair? This will be clear once we discuss Poisson bracket. We will discuss that later, but right now you have to understand that generalized coordinate and generalized momentum, these are canonically conjugate pairs, and dimension of generalized coordinate times generalized momentum, dimension of this is equal to dimension of angular momentum. Now let us define some quantity which is called action. So action is denoted by S, by the letter S. Action S is equal to integral Ti to Tf, some initial time to final time, L dt, where L is the Lagrangian. One thing to note here is that in order to calculate S, we have to express generalized coordinates and generalized velocities in terms of time, because we are integrating with respect to time. Now, why do we define this quantity action S all of a sudden? What is the importance of this quantity? The importance is in the fact that we encounter this quantity S in Hamilton's principle. Now, what is Hamilton's principle? Hamilton's principle states that it states that among the infinitely many paths available, the actual path chosen by the dynamical system is the one for which the quantity integral Ti to Tf L dt is an extremum. So we see that in Hamilton's principle, this quantity integral Ti to Tf L dt is coming. This is nothing but action. So the importance of action lies in the fact that it is coming in Hamilton's principle. From Hamilton's principle, together with variational principle, which is part of functional analysis in mathematics, we can derive the Euler Lagrange Equation of motion. If you don't know how to derive Euler Lagrange Equation of motion from variational principle and Hamilton's principle, you can type this in ChatGPT and it will give you all the complete steps required. Derivation is not as important as application in case of competitive exams. Therefore, I am writing the Euler Lagrange equation directly. The Euler Lagrange equation is d by dt of del L upon del Qi dot minus del L upon del Qi is equal to 0. This is the Euler Lagrange equation when Lagrangian is a function of Qi dot and t. Now sometimes Lagrangian can be a function of Q double dot as well. Lagrangian can be a function of qi, qi dot and qi double dot as well. In that case, the equation of motion is d square upon dt square del L upon del qi double dot minus d by dt of del L upon del qi dot plus del L upon del qi is equal to 0. Now I have solved a couple of problems already from the theory that we developed here. I will put a link to that video in the description section of this video. If you found this video helpful, please consider liking and subscribing the channel as well. We are building something awesome here. Thank you for being here. Thank you.